Hi everyone, thanks for checking out this video, and also sorry I haven't made a video in a while. I've just been kind of like really busy with grad school and stuff, but I thought I'd make one today, and I thought for this one I would like to just do some more practice with you guys on the Gillespie algorithm. So we'll be doing another Gillespie stochastic simulation, and this one's going to be a little bit more practice with a model of the growth of a cell population. But we're going to be doing something new this time. So something I haven't done with you guys yet is actually normally the ones I've done in the past, we've been kind of like plotting the time series trajectory of the variable in the simulation. But this time what I thought I'd do is I'd show you guys how to plot the distribution of the results across like many different runs of the simulation. So we're going to be, instead of like plotting the time series at the end for the variable, we're going to be plotting the distribution of the results. And also, I think there was a comment on one of my other videos asking to see a stochastic simulation of a multimodal system. So I've made this one. This is going to be kind of like killing two birds with one stone here. So this is going to be more Gillespie practice, and also this is going to be a bimodal system. So you guys will see once we plot the distribution, it's going to have two modes, which we're gonna see. Okay, so this is going to be the system we're going to be working with. This will be, like usual, I'm showing you guys the ODE version of it. But then remember, we're not actually doing an ODE simulation. We're doing a stochastic simulation. So this is like what the ODE would be if it were deterministic. But this is going to be the actual setup of the Gillespie simulation, which is related to the ODE, but it's like the stochastic version of it. So we're going to have our variable x, which will be a colony of cells. So x is just storing the number of cells in the colony, and it's going to grow with some rate r, but it's going to have this whole term here is what's called the logistic growth term. So if you guys haven't seen this yet, I recommend checking out my other video that's specifically about the logistic growth model. But just to give like a brief review here, x is going to be growing, like start off growing exponentially, but we have some parameter k here, which is a carrying capacity. So once x gets closer and closer to the carrying capacity k, the growth will actually slow down. And then it'll sort of level off when we get to the carrying capacity k. But again, that's like a quick review. But if you want to hear more about this, I recommend checking out my other video that I'll link to in the description too. My other video on the logistic model of population growth. And then just to make the results look nicer, I've actually added another cell death term here. So normally with the logistic growth model, like this, the negative part of this would be like the cell death term. But just yeah, I wanted the distribution at the end to kind of look nice and to sort of really be a good bimodal example. So I added this term here to kind of like bring out that second mode in a more visible way here. So this gamma here will be some other death rate, like in addition to the negative part of the logistic growth model. We're going to have some extra death rate gamma here that's being multiplied by whatever the current count of the cells is. And then so like usual, to set up our Gillespie model, we just, so basically to get this, we multiply this Rx out across both of these. And then once we have this multiplied out, then we just take all the positive terms in this equation and we put them here that in this rate here, which corresponds to x going up by 1. And then all the negative terms here, we just take them and we put them here, which corresponds to x going down by 1. And then also, just something to remember, when removing the negative terms down here into the rates column, we make them positive because the negative is already being accounted for over here with x going down by 1. So we don't want a double negative. We just want the positive terms here. And then that'll correspond to x going down by 1. And I'm kind of reviewing this like quickly here. But if any of this is seeming like confusing or new to you, I'll link to my video on the basics of the Gillespie simulation too, if you want to check that out. I'm kind of quickly reviewing here just because I've done it in a couple other videos. So okay, so that's kind of the setup. So let's get started with the code. So like usual, I just start off by importing the things that I have to import. So I know it's kind of confusing, like three lines here just to get matplotlib. But that's, for some reason, it's just my computer, when I got the new Mac OS update, I kind of have to do it this way, otherwise I get an error. But yeah, so I just have that, getting matplotlib imported, and then NumPy, and then the random library. Okay, and then now we're ready to get started. So I'm going to be doing things a little bit differently this time, because usually we just kind of get right into it with the Gillespie simulation. But this time, since to get the distribution, I'm going to be like calling it a bunch of times and running the simulation a bunch of times and collecting all the results and then plotting the distribution of the results across like 100 or 1,000 runs of the simulation. So in this case, instead of just getting right into the simulation, I think it actually makes more sense to put it in a function, so that we can like call the function a bunch of times without having to, put all of it inside a big for loop or something. So I'm just going to put all of it in a function this time. So I'm going to call the function grow colony, because we're talking about a cell colony here. So it's going to take 3 arguments. So the first argument will be the x array, which will be the array where we're storing all the values of x, which remember is just the counts of the cells in the colony. And then it's going to take a params array, all of our parameter values, and then tn. So that'll be the end time of the simulation. Okay, so these are going to make more sense once we go to actually like call the function. But you guys can just like take my word for it now. So when we go to define our parameters, it's just going to be our parameter r. The growth rate is just going to be the first item in this params array. And then k will be the second argument in the params array, and then gamma will be the third. And then we're going to start off, remember, and by the way, sorry if I'm going through this kind of fast, but if you guys sort of want a more in-depth explanation, I'll link to my previous videos on the Gillespie simulation, where I sort of went more in depth on it and like explained step by step. But I'm sort of with this video, I'm kind of assuming that you guys have already know the basics and already like kind of understand if I go through it quickly. But again, if anything's confusing, I'll link to my previous videos where I sort of go more in depth on each step of it and explain like more in depth. But for now, I'm just going to kind of hope you guys are okay if I'm kind of going through it kind of fast. But yeah, so like usual, our array t is just going to be where we're storing the time points. Because remember, with the Gillespie simulation, we randomly pick the next time point, and then we randomly pick which reaction will happen, and then update the variable accordingly. So this is going to be a dynamic array that will be appended to. So it's going to get filled up kind of like each time we just add the next time point to it. As we're going through the simulation. So it's going to end up looking maybe something like that, where it's just every time the simulation is updated, it'll just be appended to with the latest time point. But we start off with just time 0. Okay, and then like usual, yeah, we're going to put have that actual simulation running in a while loop. So we're going to say while the last value of t is less than t end, and while the last value of x is greater than 0. And you're going to see why we need this to be a condition in a second. So, so an intuitive thing is that if x is 0, then it's just, you can see in like even the ODE, if x is 0, it's not going to be able to increase anymore, because it's just, one of the steady states is going to be 0, because if x is 0, then the whole value of the differential equation will be 0, which means no change is happening. Also, by the way, I should tell you guys, if you want if you want to like solve this algebraically, which I encourage, this video isn't going to be like an algebra lesson, so I'm going to leave this as kind of like an exercise to you guys. But if you guys want to solve algebraically to find where the steady states are, which I encourage, like kind of obvious, one of them is 0. But then if you want to solve for the second one, normally if we didn't have this extra death term here, normally the second steady state would just be k. But now that we have this extra death term here, I encourage you guys, like as an exercise, to kind of prove it to yourself. You can solve for what the steady state will be if you just set this equal to 0 and then solve for x. And that's how you can solve analytically to find the steady state. But as you're going to see, we can also find it. Just by doing the simulation too and plotting the results. Okay, so getting back to it. So we're going to run the simulation while the last value, while the last time point is less than t end, and while the most recent value of x is greater than 0. Yeah, so while that's true, we're going to say current x equals the latest value of x. And then, like usual, we're going to put all of our rates in a rates array just to kind of keep track of them. So those rates are just coming right from here. So the first one is going to be r times current x. So again, that's the rate of this event happening here, x going up by 1. And then the second rate is going to be all of this. So it's going to be r times current x squared over k, and then plus gamma times current x. Did I get that right? Yeah, okay. So we have all the rates in this rates array, and then kind of just, going through the usual steps we usually go through. Again, if you want more of like an in-depth explanation, I encourage you guys to check out my previous videos. They're kind of like the intro videos on the Gillespie algorithm. But here I'm kind of breezing through it, kind of hopefully assuming you guys have hopefully already seen those. But so the next thing is we need to calculate our rate sum, which is exactly what it sounds like. It's just the sum of the current rates. And remember, since the value of x is changing at each iteration of this while loop, the values of the rates are also going to be changing. So that's why these need to be like recalculated every time. Because even though the parameters are constant, all this kind of depends on the current value of x. So that's why we need to like recalculate the rates every time and find the sum each time. Okay, so now that we have the sum of the rates, we can calculate our next time point. So if you guys just remember, like with the Gillespie simulation, it's really like two fundamental parts. So it's based on like calculating the time point of the next reaction and then choosing which reaction that will be. So our first step here is finding the time point of the next event. And by the way, I'm just using the terms like event and reaction kind of interchangeably. Hope that's not confusing anyone. But so to find the next time point, we just find some tau to add to the last time point. So we find tau by taking a draw from an exponential random distribution. Where the mean is 1 over the rate sum. So that's all I'm saying here is we're choosing tau as a random draw from an exponential distribution where the mean is 1 over this rate sum we just calculated. And so again, if you guys want to see intuitively kind of why we're doing that, I encourage you to check out my our previous Gillespie videos. But for now, you guys can kind of hopefully take my word for it. And then, so once we have this tau, we're just going to say t append whatever the latest time point was plus tau. So this is choosing our next time point. The time point when the next reaction will happen is just going to be whatever our current time point is, that's this here, plus this tau that we just randomly picked. So this will be the time point of the next event that's going to happen. So after we pick the time point of the next event, we need to pick which event that will be. So we're going to say, we're going to pick another random number. This one will just be a uniformly distributed random number between 0 and 1. So we're going to say rand equals random dot uniform between 0 and 1, and then we need to choose which reaction, or sorry, which reaction or like which event it'll be between these two possible events. So the way we're going to do it, like usual, is we're going to say if our random number times the rate sum is less than or equal to the current value of the first rate, then we're going to say x dot append our current value of x plus 1. So this is basically the way we're picking which event will happen is we take a random number between 0 and 1 and multiply that by the rate sum. And then so we have that like randomly chosen product, and then we just see where the product falls, like between cumulative sums of these rates. So this would make more sense maybe if we had more possible events, and you could check that out in my other videos where we had like more variables and more events. But here we're basically saying if this random product is less than the current value of r times x, then we're picking this first event to be the event that happens. And if not, then we pick the second event. So basically we're just, the way we choose which next event will happen is we just take a random choice between these two events where we weight the probabilities accordingly. So that's just kind of the mechanism of how we're picking which event will be the one that's happening at this next time point. So we check that condition, and if it's true, then we know that the positive event is happening. X is going to x plus 1. But if not, if it's false, then we know that since there's only one other choice, we know it must be the only other possible event, which is x going to x minus 1. And yeah, I realized I could have just put, instead of calling the index here, I could have just used current x since we already defined it. So a little bit of like sloppy, redundant code on my part, but whatever. I guess I'll be fine for now. But yeah, so I hope this makes sense. So this part here is just picking which event will be the next one that happens at this new time t, like current t plus tau. So we pick the time point of the next event, and then we pick which event that will be, and then we update the x array accordingly with either the current x plus 1 or the current x minus 1. Okay, so hope that makes sense to you guys. Oh, sorry, I forgot. I said I would sort of explain this more. So the reason in the code why we need this condition here, making sure the current value of x is greater than 0, is I sort of explained it like intuitively to you guys. If x is 0, then that's a steady state, and like nothing else can happen because the rates will all just be 0, and you can even see in the ODE it'll be a steady state. So if there's no cells left, then you can't really have any cells dividing, so you really can't have any events happening. You can't have any dividing, can't have any dying either. So because there's just nothing there. But the reason in the code why we need to have this condition is that if the current value of x is 0, then we're going to have the sum of the rates is also going to be 0, and then we're going to get a divide by 0 error here. So if we don't have this condition like explicitly stated in the while loop conditions, then we're going to, if x does ever reach 0, we're going to get a divide by 0 error here. So that's why I'm just kind of like preemptively taking care of that in advance. But so if x ever does reach 0, the while loop will just be discontinued, and it'll just be returned. Like however it is, with x being 0. But yeah, so and then the last step. This is basically all the simulation here, and then the last step is just to return our time point array and our x array. So we're just going to return these arrays as the output of the simulation. Okay, so that's basically all of the Gillespie simulation there. But then, so like I told you guys, so in previous videos, we've kind of been like plotting the time series output of the random variable. So we just plot like one simulation and just plot it over time. But this time I'm going to be doing something different. I'm going to be showing you guys how to plot the distribution of the results. So let's say that we want to just run the simulation a bunch of times and have some cutoff time where the simulation ends. And then we want to plot the distribution of what x is at that time point. So the way we're going to do this is we're going to, well, I'll just start showing you guys. So we're going to have some arrays starting off empty, just called cell counts, and then we're going to set up a for loop just with however many times we want to run the simulation. Just put that in here. So I'll start with like 1,000 times, and then so we're gonna so we're just gonna basically just in this for loop we're gonna each iteration of it we're gonna run the simulation, and then we're just gonna like save the output at whatever time point we're interested in, and then after that we'll plot the distribution of x at that time point. Okay, so we're going to start off by defining our initial condition of x. So let's make that, make that 1. Start off with 1 cell. Because remember, if we start off with 0 cells, just like nothing's going to happen. Because you need to have at least 1 to have some of these events happening. Because if it's 0, you can't really have any cells dividing or any cells dying. So we're going to start with 1 cell. And then, let's define some of our parameters. So R will be 1. K will be 100. Gamma will be 0.05. And then just for keep things organized, you're just gonna put all of the params in this params array here. Okay. Oh, and then our t end is going to be 12. Okay, so we have all of our params and stuff set up. So now we're going to actually call our function. So this is why I wrote in a function too. Like I didn't want to, because otherwise, I mean, we could just put this whole thing into the for loop, but I just think it's easier just when we're doing this stuff to just have a function defined. Okay, so we're going to say t out x out equals row colony. Remember, that's our function name, and then passing in the arguments x in. That's going in here. That's our x array. And then params. It's our params array there, and then t end. Okay. And then so this will just run the Gillespie simulation, and we'll get our time point array and our x array as the output. And then so we're going to then append to this cell counts array. We're just going to append the last value of x out. So basically, at the end of the simulation at t end, whatever x ends up as the last element, like the most recent in the simulation, at t end, we're just going to append this final value to the cell counts array. Okay, so this is how we get the distribution. So it's just this simulation is going to run 1,000 times, and then each time whatever x ends up as is just going to be the final value of x will be appended to cell counts array. So now we have all the final values of x in this cell counts array. Now we want to visualize it, right? So we want to actually see, because this is kind of like, in some ways, this is kind of like the whole point of this lesson is showing you guys how to actually like visualize the results. So to do this, we're going to use the matplotlib hist function. So we're going to say plt.hist cell counts. That's the array with the distribution that we want to visualize. And then we're going to say, this part's a little bit tricky here, but we're going to say bins equals np.max, the max value of the cell counts array, plus 1. So basically what this is saying is that we want to have a bin for each possible value of the cell counts. So there's no decimals involved here. Like the cell counts, it's all going to be integers. So it can be 0 up to whatever the max whatever the max cell count recorded is. So that's why I need the +1, because it's like because 0 is also a possibility. So it's the possibilities are 0 and then all the integers up until the max recorded cell count. And you guys don't even have to do this. You guys can set the bins to be whatever you want, or just set it to the default. But I just think this is kind of like the best way to do it. It makes the most sense is to just have like one bin for each like possible integer that it could have been for the count. Okay, and then plt.show. And then, yeah, so from this we should get a pretty nice histogram with the distribution of results here. So hope I didn't make any mistakes or anything, but yeah, let's try this out. What do I call this again? Oh, yeah. Oh, whoops. Okay. Sorry, guys. Forgot in here. Okay. Oh, another error. Okay. Sorry, guys. Oh, yeah, here. Okay. No, sorry about that. Mixing up the variable. Okay, yeah, so you can see the results here. So we get this this nice histogram of the distribution. So it's like I said, like, so part of the reason I chose this example was because there was a comment I got on a video asking about multimodal multi-model systems and how to do the stochastic simulation of them. So as you can see here, we have two modes around each of the steady states. So we have a mode at 0. And then we have a mode at, again, you guys can solve analytically, but I'll just tell you it's going to be a little bit less than k. This other steady state is going to be a little bit less than whatever k is, and you can solve analytically to kind of prove it to yourself. But you can also just see, you can kind of see in the results here, it's going to be a little bit less than our k was what, 100, right? Yeah, so the k is 100. If you solve analytically for the second steady state, you're going to find that it's a little bit less than k. So, but yeah, you can see it here. So, this is what it looks like when we're kind of getting like a bimodal distribution of the output. And yeah, so this is kind of what's to be expected. Because, I mean, if you think about it intuitively too, so with the cell colony, there's basically like, when you start off with one cell and do this experiment, there's really two things that can happen. So it can either like the cell dies before it really gets to the full colony size, and it just dies and it gets down to 0, and then that's it. Because remember, once there's 0 cells, you're not getting any more cells out of that. You know what I mean? Or if it doesn't die that quickly, it can grow out into like the full colony size, approaching something around the steady state. So that's why we have like two modes here. That's kind of the intuitive explanation. And then if you guys wanted to, yeah, I encourage you to like, I mean, obviously one of the steady states is going to be 0, but I encourage you to like think mathematically about it too, about how each of the modes corresponds to one of the steady states in this ODE even. And yeah, this graph's still a little bit kind of choppy, so maybe I'll just show you guys like one more. I'll just instead of 1,000, I'll try it like 10,000 runs of the simulation, and we'll just see what this looks like too, just for fun. Yeah, this one's probably going to take a while, so I'll probably just end up like cutting some of the video to skip to it. Okay, so here's the results after what was it? Oh yeah, 10,000 runs of the simulation. So as you can see, it's like even smoother of a plot here. So we can really see the two modes nicely. So one of them just at 0, and the other one at our second mode here, which you guys can again like I said solve for algebraically, but it's going to be like a little bit less than k, the carrying capacity, a little bit less than that. But yeah, so that's basically it for this lesson. Just kind of like showing you guys how to how to plot the resulting distributions of the Gillespie simulation. Um, yeah, so that's really it for today. So let me know if you guys have any questions or anything. And like usual, I'm going to be putting the code up on my GitHub if you guys want to download it and try running it yourself. But yes, that's it for today. So thanks for watching, guys, and let me know if you have any questions or anything. But yeah, thanks for watching, and see you next time.